Thank you very much. Good morning. Hi. It's getting almost noon, but my name is Ei-ichi Negishi, and after a brief moment of debate whether I should use English or Japanese, I finally decided to use English because, in my opinion, today anymore, in the whole world, English is about the only common language. So, noticing that there may be more Japanese here, I was tempted to use Japanese, but forgive me. And also, I have to make another excuse. We have just completed 20-year-old research on how to synthesize all kinds of chiral optically active compounds, but I need about 1 hour, and I reserve that for my next lecture 2 days from now. So if you're interested in, please attend that part of my lecture. And today I will talk about my lecture primarily for high school students. I'm sorry. Okay, let's begin. And I call this, and I emphasize the significance of ABC guidelines. Very primitive, but very I believe they are all very important. A stands for ambition. So I say, just like some famous person, boys be ambitious. I think we should be, as a scientist, we should be ambitious. And people ask, how ambitious should we be? Well, I say, as ambitious as you could be, one could be. I think you can always be more ambitious. And I will briefly explain with what is shown here. And my B word stands for two things, broad and basic. I think basic may be more important, but as a scientist, what we do should take care of or establish or bring about some new basic science. And I think Nobel Foundation also emphasized this part. And broad, not just be able to use this case or that case, but in all kinds of cases. So let us be broad and basic and broad. And third thing is, of course, we have to be creative. Of course, we learn something from many other of our predecessors. But be that as it may, I think we have to bring, our own creativity. So we try to be as creative as possible. Of course, these are easy things to say, but unless each of us is fully committed to all these keywords guided activities, or if we did, then many good things, I believe, will come out and make this world a better place to live. Okay, so with that, I decided to skip altogether what we have just achieved. That is to be able to synthesize all kinds, or any kind, maybe a little overstatement, all kinds of chiral compounds, as pure as you want, you wish. By this I mean far higher than 99%, of course. 99.69, 99.9999, or 79. And I asked my pharmaceutical company friends, how pure can should our compound be to be completely safe? In other words, not affected by small amount of contaminants. Then he said, well, 6 nines are okay, but sometimes not so, we are not so sure. But 7 nines and above, even a minor amount of toxic materials, I'm just quoting, may begin ceasing to be toxic. So, but I claim today, now, we can jack up the purity level as high as needed. And I'm talking about 6 nines and 7 nines. But what you see here may show something like a greater than 98 or 99% EE. Sorry, today I don't talk about that. If you are interested in this, 2 days later, there is my 60 minutes lecture in Tokyo. So with that, I'd like to excuse myself. Okay, let's go back to this ABC guidelines. Ambitious. And let me see. Okay. Well, first of all, how should we synthesize any organic compounds? Well, in my opinion, in high yields, highly efficient way, selectively, economically, safely. And a la President Obama, I say, yes, I want to say that, but I have never found the second why. There aren't many why words. So I say, yes. Okay. So that represents this YES. And of course, these are self-explanatory. So I won't say much about this. And the question is how to achieve these kinds of organic synthesis in a general way, in a predictable way, economical way, and so on. Well, I believe that we should go back to Mendeleev. This is the universe. So Hayabusa and those universe exploring vehicles are used, but they haven't found anything yet beyond 113 or 14, I forgot which. But anyway, 113 or so shown here. Then as you can see, here's the basic screening or knowledge. Okay, so how do I point? Okay, this is the pointer. Okay, sorry. So you see, after this polonium, beginning with the polonium, all these are fully red, radioactive elements, 26 of them. In organic synthesis, in some special cases, we may use them, but in the main, we should stay away from them. That's how I feel. And then, of course, these gray inert gases are useful, but they don't participate in organic reactions per se. So we should acknowledge that. And then there are some red framed 1, 2, 3, 4, 5, 6, 7. Beryllium, intrinsically toxic. Cadmium, all Japanese know, itai byo. We should not use cadmium, except in a very, very, very special cases. Mercury, likewise. Unfortunately, original version of Professor Heck reaction used the mercury in a stoichiometric amount. Anyway, thallium. So, and the lead, and tin, and arsenic. So these we avoid in the main. Okay, what else? Then we are left with about 10 to dozen green elements. Those are used to form organic compound, to construct organic compound. We must use them. Okay, 10 or dozen. And then these blue ones, about 20 some shown here, 21, main group metals. They are relatively cheap and relatively safe except for some of these. So we use them. Then what else should we use? So my notion here is that we should use all of the available elements that are usable, as we are now discussing. So what else? Then I realized as a graduate student at the University of Pennsylvania, so here 3 times 8, 24. Take away this technetium. 23, yellow color. No, it's not yellow. In my mind, it's a golden color. Okay. They are extremely important. They have helped me build my career, believe me, half a century. So these elements, yes, indeed, they are expensive. Gold, platinum, palladium, iridium. But I just mentioned these 4. Do you know that we all must depend on them every day? And you know that. They are used to clean the poisonous gas like a CO and NO and so on. And in the dirtiest part of the car, we have a small amount of these. And I hope, we virtually never replace that muffler, this device, as we drive maybe 5 years, your car. In my case, maybe I will keep retained for 10 years. But they keep working. So fantastic catalysts. And of course, I don't need to explain further. So not because these are intrinsically expensive, we can never say. Probably they are serving as some of the cheapest, least expensive items for us to keep our world in a living environment better. Okay, so this, I hope, will persuade you, and of course, most of you here already knew how important these transition metal elements are. And regardless of their raw, how should I say, cost per gram or per mole or whatever, because many of them can serve as a fantastic catalyst that can turn over millions and millions of times. So, as a PhD student at the University of Pennsylvania, around 1960 to 63, I became very much interested in these elements, but I didn't know how to use them. Anyway, so here it is, one of my greatest heroes, Mendeleev. In Moscow, there's St. Petersburg, I think. Moskovsky Avenue, there's a Mendeleev Institute. And I was astounded by finding that already about 90 out of 112 or 13 elements known are shown here. And of about 90, he discovered 11 of them. More than 10%, or even now, about 10% of the universe. And of course, I'm not speaking ill of Madame Curie, but Madame Curie received 2 Nobel Prizes for credited with the discovery of 2 radioactive elements. elements. And on that basis, I want to give this, this individual person 11 Nobel Prizes. But he just came a little too early, half a century too early. But I think we should recognize this. And the way he discovered 11 of them, he started, I think this periodic table was his creation. And he would leave some holes, and then the holes, where he found the holes, 11 of them, he said there should be element here that we are not familiar with. Not only that, he predicted some properties, like the densities or some chemical properties, judging from the properties of the surrounding elements. Very, very scientific way. Anyway, so let's go back to this. Okay, so this one. Let me see. I want to go, yeah. This picture on the left, this is the chemistry that Nobel Foundation kindly recognized for us. And here I am showing organic compounds just as R1 carbon group singly bonded to another carbon group, R2. So many, many, many organic compounds can be represented by this yellow box. And then the question was, how should we synthesize all these things? That was a question I had when I was 26, sophomore, the second year in my PhD program at University of Pennsylvania. And then I came up with this Lego game approach, Lego game. So Lego game invented in Denmark, I believe, had just invaded all over the world. So in a Lego game, you need some piece with a hole, maybe acid, and another piece with a stick. Then the rest of the part can be anything. Okay, and then they can just snap. As long as one has a hole, the other one has a stick. Aha, if we can synthesize organic compounds in this way, this could be a very, very generally applicable method. That's what I thought when I was 26. And 26, and I became assistant professor at the Syracuse University when I was 37 already. Sorry. Anyway, many years later. So, but this Lego game notion became the foundation of our cross-coupling, as I can just show you. So here is organic halides, or X being these kinds of electronegative elements. R1 is plus, in other words, electron deficient. And we need a second piece, R2M, metal, as I have shown, just 20-some main group elements and 20-some transition metals can also be considered here. As shown here, zirconium is a transition metal. So, and if you make these two kinds of things, I thought they should snap to make this one, but that was not the case. We needed one very, very critical reagent. That is this transition metal, preferably D-block transition metals, 23 candidates. And we ended up choosing first Tamao's nickel, but that had a limited applicability. Oh my gosh. And palladium eventually became our choice. So here they can do so-called oxidative addition reaction. Then this can exchange X with R2, and then the two different kinds of groups are grabbed by transition metals. But they can be readily decomposed to release what we want. And the rest is this, so it goes back, so it goes around and around. Okay, so in view of time, I should rush. And so that was the notion. And without the catalyst, when I was a first-year student, I got this Lego game idea, and I wasn't considering a catalyst, use of catalyst at that time. Without a catalyst, what I found was a miserable picture. So these are about 10-ish organic, various organic kinds of organic electrophiles and organometals, namely nucleophiles. So if we can hook all these, everything, about 100 of them, 100 different kinds of them, then we would be in business. But what I discovered through the literature, extensive literature work, mainly using magnesium here, no catalyst, then miserable picture. These things don't work. Some of these may work, but not very good. Now, after introducing D-block transition metal catalyst, same matrix, mostly green, and then these yellow ones, even yellow ones, Greg Fu, now Caltech, and Buchwald, and so on, they are making this one greener and greener and greener. So we can now change this color a little bit between yellow and green. So there are some areas that are still troublesome, like red framed one. We don't need to do this to make these compounds. We do this, and this is green. So, as some people say, this method can be applied to a wide variety. And my last part of my talk is why metal? Why D-block transition metal? And I will stop my lecture. So if you mix 8 electron alkanes with alkenes, 8 electron, no facile reaction. But if you can manage to convert this one into carbocation, 6 electron species, then bingo, it will react very rapidly. So the significance of this empty orbital. Okay, but now hydroboration of my Professor Brown, is sort of an isoelectronic kind of reaction, as you can see. 6 electron. This reaction is very fast and more equally important. This addition of B and H, 100% cis addition. 100% cis addition. And a little later, hydrozirconation was discovered. And this one is, zirconium is a D-block transition metal. So here we counted up to 8, but here we have to count up to 18. So this one is with empty orbital, 16 electron species. But if you look at this part, they look alike. Anyway, no wonder hydrozirconation reaction works also in the same way. Much more recent discovery. And yes, you're right. This reaction is essentially 100% syn addition. Just boom. Okay. So now you got this. And there is a very, why do we need a catalyst and so on? Here is the thing. If you just mix acid with base, they come together, and then these kinds of simple acid-base reactions are surprisingly of high energy processes. And the people have wondered. Actually, one of the best report is rather recent. Let me just briefly explain. Acid and base, they come together. They come closer. And then as base begins to transfer some electron to form a bond between A and B, A will become negatively polarized, as you can see, become more negative, because it is beginning to accept the electrons. Now, as B begins to send the electrons, then it will become positively polarized. What are the effects of these polarization? Well, this negative charge will say, don't come. Go back. It was, first trying to bring it, but now it says, don't come. B says, don't go, come back. You see that? And that is shown here, as Sharma Professor explained. And so at one level, two electron transfer reaction can be a very high energy barrier process. How to resolve this? So here it is. I would say this one started by Fukui. Just give me 1 minute. So 2-level, 4-electron process. 2 up, 2 down. Let's just think that way. So Fukui was the one who introduced and emphasized the significance of LUMO, lowest unoccupied orbital, right? LUMO. So actually, alkene, we normally talk only about double bond, but above this, he said, empty orbital of this symmetry. Then if metal is configured this way, 2 electrons can go up, and outside the d block transition metals have these kinds of orbital. They can back donate to pi star orbital. Before Fukui, probably nobody thought about this pi star, empty orbital. So 2 up, 2 down. Why is it good? We saw this ill polarization effect. Directions are different, so they are all but cancel. So the overall process becomes very, very smooth. So this is one of the very, very, very important and generally applicable principle. I said Brown's hydroboration works so fast, so well, so selective, 100% sin addition. 2 up and 2 down by considering Fukui's LUMO explained. So I thought maybe this hydrogen can be replaced with anything. Hydrogen can be replaced with carbon, and I even named it before I discovered any reaction. Carbometallation, hydrometallation, carbometallation. But in the periodic table, there are more elements. Halometallation, or maybe metallometallation, whole bunch of metals, several halogen. Today, we have everything, believe me. And as you're right. All those kinds of reactions that can be explained in this way, they are essentially 100% sin addition. So this is now if you, by thinking in a broad, basic, and scientific way, you can discover, I think we have discovered all these before they were discovered. So that's my key message. And this is a generation of superacid species, but I don't have time. Professor Yamamoto is doing this. And I think that's the end of my story today. Thank you very much.